Hello everyone. So we have this example, determine the structure stiffness matrix for the two-member truss shown. And AE is constant. So here we have a structure. First of all, we have 2 points to solution. First one is establish the X and Y global system. That's mean we have this joint number 1. This is X and this is Y. This is X and this is Y. And for number 2, Y and X. Also, you can give it a number. So because it's for easy calculate and easy understanding, I can start number here when we have a free joint, like joint number 2. X in a joint number 2 is number 1 and Y is number 2. This is number 3 and this is number 4. This is 5 and this is 6. It's actually up to you. You can do this is number 3, for example, and this is number 4. 1 and 2 is up to you. But to make it easy, because actually we have, as you see here in this figure, joint number 1 and joint number 2 is fixed. So the displacement is 0. And we have also applied load at joint number 2. Because when we applied the load on joint number 2, our system or our truss, it will be like this. So we have displacement at Y direction and also in the X direction. We have displacement, and this displacement is unknown and we will find it. Second point is identify each joint and member numerically. So this is member number 1 and this is member number 2, and also I put it directions like here from joint number 2 until joint number 3. This is near point and this is far point, and also from 2 to 1 this is near point and this is far point or node. Also you can draw the directions like this. It's up to you. How we can put I'll give a number of the joints and of members and the direction and also the global is actually up to you. And for node number, near node and far node, to calculate the lambda X and also lambda Y. So now in the next slide, actually we give the global X and Y and the directions as you see here in this figure. For FK is mean noun force. So we have this force applied on joint number 2, and the FK is on X direction. Start with X direction first. We don't have any force applied on truss, so it will be 0. And also we have 2 kN kilonewton applied on Y direction. So because it's applied to down or push its structure to down direction, so I put minus 2 and give it this one number 1 and this is number 2, because I already give this one is global number 1 and global number 2 on joint 2. And as I said before, KD, that's mean noun displacement, is 0 on number 3 and number 4, 5 and 6, because it's fixed from these point or these nodes. Here now, actually I will calculate each member alone. So I will start with number 1, and this is my member number 1. Here, as I mentioned, this direction, this is near point, and let me to throw here. This is near node and this is far node. So for Linda X is equal X far minus X near divided by L. L here is the length of member. We have 3 feet. This is the length. And XF is mean the end of member. How much is? It's a 3. This is 0, 0. And this is 3, 0. And joint number 1 is 3, 4. So if I take the X far here is 3, as I put it here, minus xn is 0, divided by L, so equal 1. This is Linda X. Linda Y is equal, because the hour member is horizontal, so it's already the, let me to see, Linda Y, Y far minus Yn over L. L is 3, the length of member, and YF is 0 because it's a horizontal member, and the Yn also is 0, so it will be 0. So now we have to put all values, our values, in a matrix now. AE is constant, and L, you can make it outside the matrix as it's here, or you can put it inside the matrix. And a perfect way to make not from any, to keep yourself from any mistake is put L inside matrix. That mean, for example, here as I put here, Linda X square over L. That's mean all or each Linda is divided by L. So on and so forth. Okay? Is divided by L. So, sorry. Now, just I put the Linda X square. Lambda x square, it's already, I have 1, and divided by L, it's mean 3, it will be 0.333. I put it here, and lambda x and lambda y, that's mean lambda x is we have 1, and lambda y is 0, so it will be 0. Lambda x, minus lambda x square, it will be minus 0.333. This matrix, it's constant matrix, and it's constant location of each lambda. Beside that, we can do the numbers, put it the numbers of the global system. That's mean here we have xn, xy, fx and fy, and same it's, but I will done it's like a column, nx, ny, fx and fy. So here nx, and this is nx, it will be equal lambda x square, and we already calculate it. It's 0.333. Same with ny and nx. We have lambda x times lambda y, so it will be 0. Also, the fx with nx minus lambda x square, so minus, and lambda x square is equal 1, and 1 over 3, it will be 0.333. And also it's same to with the others parts or members of matrix. Now with the number 2, this one, lambda x is equal x far minus x near divided by L. The x far is 3, as you see here in the figure, and the x near is 0, because this is the near point and this is the far point, or not, and divided by the 5. 5 is mean the length of member number 2. How we can find it is 3 square plus 4 square equal 25, and equal 5. This is the length of member number 2, because it's an inclined member. And for lambda y is also same. Y far minus y near over L. Y far is 4, and yn is 0, because the joint number 2 is 0 by 0. Okay. Divided by L, it will be equal 0.8. Same way and same the structure of matrix, we use it, this one. And please also the L should be put inside matrix, is easy to calculate. because when we collect the matrix number 1, that's mean k number 1 and plus k number 2, already we have a different length. As you remember, the length of number 1 is 3, and the length number 2 is 5. So maybe will face it some confused when we calculate the K1 and K2. So it's easy for us to put it L inside the matrix. So now just calculate or collect the nx with nx and ny with ny and so on. Here also, or you can give the number of a global. It's easy for everyone. I can put it because this is, as I mentioned before, this is the global number 1, and this is number 2, and this is number 5, and this is number 6. So here the nx is mean the near node on x direction is number 1, this one, and ny is number 2, and also for fx is equal 5, number 5, and with fy is number 6, and it will be same with the numbers, but same numbers, but put it is by a column or vertical size. Now we collect all the members of matrix of K1, stiffness of member number 1 and the stiffness of number 2. As you see here in this slide, and when we calculate, put it this 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, 6. How can I sum these members? I will take one by one. This is 1 by 1 0.333 plus 0.078. It will be 0.405. Now I can take, for example, number 2, 0, I have 0, 2 with 1, this is number 2, and this is number 1. Same, I will search about 2 global, this is 2, and this is global number 1. So 0 plus 0.096, it will be 0.096. Let me to take another one. For example, here 4 with 5. This is 4 global, and this is 5. We have 0 in member number 1, and we search in member number 2 about 4 and 5. So this is 4 and 5, it's equal 0. That means 0 plus 0, it will be 0. It's just when we sum the matrix, just follow the number of global system that we give for each one. Now, how we can find the the displacement? This is the K matrix that we find it by K1 plus K2 in the previous slide. Now, actually, F equal K times D. D is unknown for number 1 and number 2 is unknown displacement. And the other is displacement, it's because joint number 1 and 3, as you remember in the first slide or second slide, it's known because it's fixed, so it will be 0. And for K noun we have 0 and minus 2. So now, to make it easy to calculate only the parts that I want to find it, I will divide it, my matrix, for how can I say, it's like for two parts. Yes, horizontal side, this one. Why? Until, because I need only to find D number 1 and D number 2. And same, I want to take two values. I mean, for K11, we have two values only of, it's helped me to find D1 and D2. And also we have two values of force. So it will be like this. The K is 0 and minus 2 equal AE. AE is constant, and this is K11 and D1 and D2 plus 0. Why plus 0? Because this part K11 time multiplied by D1 and D2, and for plus the K12 time D3, D4, D5 and D6. So all this displacement is equal 0, and each number when multiplied by 0, it will be equal 0. So no need to calculate and waste our time. How we can solve this matrix to make it easy for you? This is, I call it B matrix, and this is A matrix, and this is D matrix. I want to find D matrix, so it will be like this. D matrix equal A matrix, but I will take it inverse, time B matrix, so that our values by your calculator, it will be equal D 4.505, and this is the D1, and D2 is 19.003. Here also I want to find the other forces, F4, F3, F4, F5, and 6, because here, as you mentioned in this slide, is we have only non-forces F1 and F2. So the other forces, actually we should find it by this way. I will take the other part, this one, the K21, time by time or multiply by D1 and D2. This is the value of D1 and this is value of D2, as I find these values from last slides. Plus 0, as I said, the 2, let me here, K21 time D1 and D2 plus K22, yes, time by displace number 3, displace number 4, 5, and 6, and all these values is 0. So I wrote here it's 0. So now it's easy to find F4, 5, and F3, 4, 5, and 6. Now the last part is how we can solve or find the internal reactions. It's easy by follow this rule, AE over L, matrix of minus lambda x minus lambda y, lambda x and lambda y, multiplied by dnx, dny, dfx and dfy. So here, let me try for member number 1. I say member number 1. AE is constant over L. L is 3. You can go to slide number 2 or 3. Lambda x is 1, minus 1, as we calculated when we found the lambda x and lambda y of member number 1. Minus lambda x, lambda y, sorry, is 0, and lambda x is 1 and lambda y is 0. For displacement, we have, as I remember, is this is sorry. This is member number 1, and our directions look like this. This is number 2, this is number 1, and this is number 3, and this is number 4. So the displacement is displacement number 1 is already got it is 4.505. Displacement number 2 is 19.003. Displacement number 3 is 0. Displacement number 4 is 0. This is the value of this matrix. It will be, after calculate the matrix, it will be look like this. Force for member number 1, the internal reaction is equal minus 1.5 kilonewton. This is compression because the sign of minus. And you can try in the same way for internal reaction for member number 2 is equal 2.5 kilonewton is tension because it's positive. So this is the how we can find the stiffness, or how we can find the forces by stiffness matrix. Let's move to example number 2. Example number 2 here, we have truss has 3 members and ask you to determine the force in each member of the bin connected assembly of the figure show. If the joint 1 settles 25 millimeter. So here, this is after I give the joints numbers and directions and the global. So in this joint number 1, we have settlement to down equal 25 millimeter. So here in this we take a free joint number 2 as we said here, or give number 2 for it, equal 0, 0, because we don't have any applied force in joint number 2. And for displacement noun, we have in the global number 4 here minus minus 0.025. Why we choose this global? Because settlement is usually or always worked with vertical direction. Okay. So here displacement at global number 3 is 0. Displacement with global number 4 is this one, minus 0.025. And about the others, it's fixed, so we don't have any forces or any settlement or anything's applied. So 5, it will be 0, 6, 0, 7, and 8 is 0. So now we, same as we solved it in the last example, Member number 1, we find lambda x is equal x far minus xn, or near, over L. This is the I think this is the length. Sorry, I didn't give the length of members. This is number 4 feet, and this is 3 feet. Okay. So now here in the member number 1, the x is equal. Sorry, how can I write? Let me to clean. Uh, 3 by 0, and this one is 3, 4. So xf is 3 minus xn is 3 divided by 4. So here is 0. 0 over 4 is equal 0. So this is the lambda x. Lambda y equal yf minus yn over L. L is 4, and yf is 4 minus yn is 0. It will be 1. So here, as you see, lambda y is equal 1. Now, after I find the value of lambda x and lambda y, you can go to the K matrix. We need only for lambda x square and lambda x and lambda y minus lambda x square minus lambda x and lambda y. You can go to a previous example and look it for the matrix of K matrix. Okay, and depend on these values, we have lambda x is 0 and lambda y is 1. You can put the values, and please also don't forget they give the number of global here. Depends on the far as you give it. This is direction is from bottom to top. We have 3, 4, 1 and 2. So 3, 4, 1 and 2. Start with x, y for near, and x and y for far not. Same with member number 2 and with member number 3. Same way and same K matrix. So after find the all matrix or K matrix, now we want to find force. Force equal K multiplied by D. K is K1 plus K2 plus K3. And D is displacement Displacement D1 and D2 we don't know, because here, as you see in this figure, D1 and D2 is a free joint. As we mentioned, actually, this is 1 and this is 2. So joint number 2 is free, so can move it by X direction or Y direction. And we don't know the values of these two values, but we have the force is 0, 0, because we don't have any force applied on joint number 2. And for D number 3 is 0, as we go to figure here. D3 is 0 because the settlement is take Y direction. Only on Y direction. So it will be minus, because down side or down direction, minus 0.025. And the others joint is already 0 because it's fixed. We don't have any force applied to make it a little bit changed. And this is K11, K12, K21, and K22. So here, same way, divided the matrix for two parts to find D1 and D2. Now here, F is 0, 0, and this is matrix K11 and D1 and D2. That's I want to find it. And also we have plus here, not like first example, because we don't have any settlement. So here, because we have settlement, I know it's 3D and D number 3, D4, D5, D6, D7, and D8 is 0. But for D4 here, we have a value of settlement. Okay, so it will be not 0 like a previous example, because we have this value here. So plus AE, this is K 1, 2. Okay. How we can find it is easy. Just calculate this matrix first. We will get 0 and 0.0083. Okay. And call this value, this matrix B matrix. And this is matrix A, and this is matrix D. Same way, D matrix equal A matrix inverse time B matrix. We will get the D, D1, and D2. Now go to find the force reaction. Force reaction of each member. F equal AE. AE here equal 8,000. I think it's given in the example. Yeah, in the example here, it's given A is constant is 8,000 kilonewton. So here AE is given 8,000. L is 3, the length of member 1, and Linda X, Linda Y, minus Linda X and Linda Y positive. So Linda X is 0, Linda Y minus 1, and because we have minus here, be careful. Linda X 0 and Linda Y is 1. The multiply by the D is DNX, DNF, DFX. So here Y. Sorry. Here we have DNF, sorry, Y. Okay, DNX is 0, DNY is minus 0.025. Displacement of fx, the far point, as we calculate is from last slide, is 0.00556, and the last one, this dfy, is minus 0.021875. So multiply, we will find this value 8.34 kilonewton, and this is tension. Same way with member number 2, we will get minus 13.9 kilonewton, it's compression. And try to find also member number 3. I will give to you the last value. It's equal 11 kilonewton tension. So here it's already finished the example 1 and 2, and show you how we can solve force by stiffness matrix. Thank you for kindly watching and listening. Thank you so much.